start it.
Yes, now
Okay. Okay. So again, thanks for joining in for this session. This is a second session, and we will discuss about machine learning introduction. In this session, we will discuss about artificial intelligence, machine learning, generative AI, and then the types of machine learning, supervised learning, unsupervised learning, and reinforcement learning. Then we look at scikit-learn API to build a simple model, right? And then we discuss about linear regression model, overfitting and underfitting and good fitting. Then once we have the model built, we need to evaluate the model performance. So for evaluating model performance, we look at root mean squared error and R squared. So these are the things we will be discussing in the today's discussion, right? Um, so this is the whole artificial intelligence and machine learning context, right? So um, you have artificial intelligence. Um, Artificial intelligence is basically is is to think like a human, right? Think and learn uh, like a human, right? So that is what we are trying to do with artificial intelligence. And within artificial intelligence, machine learning is there. Machine learning is basically um, with the huge amount of data given to a system, it will try to learn from the system, learn from the data actually. So instead of we give explicit rules, it actually figure out the rules based on the data we are feeding. Um, right. So we are not
Well, just
giving
a quick
explicit.
question.
Yeah. Huh?
Did you mean to be sharing your screen or no?
Um, Sorry.
That's okay. We're all on the same team.
Um,
Thanks so much. Yeah, it's a great slide. So I wanted to make sure that if you wanted us to see it, that we
uh,
could. So thank you.
um, okay. I think I was sharing and I confirmed. I don't know if this. Okay. So I have a
lost
problem.
when you switched to the recording though, so that's why.
Yeah, and probably my machine has a problem too. Whenever, as soon as it stops sharing, let me know. Okay, I'll reshare. Maybe because of the memory issue, it automatically stops sharing. Okay.
Okay, thank you.
So I don't know where you lost, but um, so I was trying to explain that we have an artificial intelligence, and artificial intelligence is basically focus on building machines which think like humans for doing tasks like reasoning, planning, and understanding language, right? The main goal of AI is to create systems that can think, learn, and make decisions the way humans do. And within AI, there is machine learning. With machine learning, we feed the data, and the learning algorithm basically figures out the rules from the data we are feeding in. We are not explicitly setting the rules um, for the machine. Machine is making up its own rules by reading the data or learning from the data we are feeding in. So that is the machine learning part. Within machine learning, we have deep learning. So if the data set is very big, right, you have vast amount of data, then it's better to use the deep learning techniques rather than machine learning techniques. In deep learning, we use neural networks. Yeah, so that's about deep learning. For self-driving cars, there is a lot of amount of data that needs to be processed in order to learn and then predict the outputs, right? So the deep learning is used there. Okay, and then generative AI is a new branch on top of deep learning. Um, Instead of just recognizing the patterns, it'll generate the content as well. So the machine learning is basically predict the output. When you give an input, it will predict the output. That's the concept of machine learning. But generative AI, it'll generate the content. After learning, it'll use that learning to generate the content. Okay, that is generative AI. And large language model is also there. Let me pull one more. Let me pull one more slide. So there is large language model, which is subset of generative AI. Large language model is trained on vast amount of internet data, right? It will continuously predict the next word in the question you are asking, right? ChatGPT is an example of large language model, right? And so it's important to know when to use which of these spectrum of the tools available, right? Let's say you want to predict, a house price given the size of the house. You can choose machine learning, right? And also you want to predict if you give an image of a cat or a dog and you want your model to predict the image you were giving, that is also an example of machine learning technique, right? So it's important to know which technique to be used and use that technique for your task to achieve, right? And these are the types of machine learning. Supervised learning is where the data set will have the input and output. Output, we are calling it as ground truth. And for the model, actually, we are providing the input and output. So it learn, and once it is learning, when we ask the model with a new data, it will try to predict. So in supervised learning, we are providing ground truth as well, right? We are providing labeled data. But when it comes to unsupervised learning, we don't know what is truth. We don't give labeled data. We just give some set of data to the machine learning model, and it'll try to segregate the data or group the data or try to find the patterns within the data, right? So one example is clustering. Um, so let's say there are a group of people, and if the machine learning model has to segregate them as groups, as who are students, and the second group can be who are software professionals, and the third group can be air hostess, right, etc. So we are not giving the ground truth. The machine learning algorithm itself tries to group the data together, cluster the data together. So that is an example of clustering. And dimensionality reduction is where, let's say you have an image of size 30 megabytes, and it has a lot of pixels of data, and you can reduce the size of the image to, let's say, 1 MB by decreasing the number of pixels, but without losing the actual information of the image, right? The 30 MB image, you can identify what's in image. If you made it as 1 MB, then also you are able to identify what is in the image. So we are reducing the number of pixels, but we are still able to identify what is in the image, right? So dimensionality reduction is the concept of, um, let's say, feature reduction, right? Why we have to do that? To get efficiency. So training a model includes a cost point in it, right? So um, if you have to train the model on vast amount of data, it'll take time, and also it incurs a lot of cost, right? So if you can still train the model without losing the accuracy by decreasing the pixels or the features, then it's great, right? So this is an example of dimensionality reduction. Uh, Actually, an example of where the dimensionality reduction can be used, right? And then we have reinforcement learning. Just a second. So we have reinforcement learning. I'm showing one more slide. Um, so over here on the right, reinforcement learning is basically learning by trial and error, right? You have an agent. Agent takes an action in certain environment, and if the action is appropriate, it'll get a reward. Um, and then it'll make the rules based on the response it is getting. Um, if the output it predicted is not right, then it'll give a signal that the output is not rewarding. Then it'll try to make the rules by itself and try to predict the next time correctly, right? So um, this is reinforcement learning. It is kind of go in loop. Okay. Let me put this too. So agent is a decision maker, and environment is an external world that the agent interacts with, right? The choices agent can make at each step is the action. The positive or negative feedback the agent receives after taking an action is a reward, and it updates its policy based on the reward, positive or negative feedback it is receiving, right? And the best example is if you ever use Gemini. If you ask a question, sometimes it will give two responses for you, choice A, choice B, and there includes a thumbs up or thumbs down too. So that's the best example of reinforcement learning in LLMs. So so that is about reinforcement learning, right? These are the three machine learning techniques, and and these are like classical machine learning techniques. We are not trying to do deep learning here. Deep learning is another lesson. So for classical machine learning, the widely used algorithm is scikit-learn. So uh, um, you you basically create a model, and then you call fit on your model. You give X is input, y is output. So we are creating the model, we are fitting the model with the data, and then we are predicting on new data. So model will predict on the new data which it has not trained on. And so this is the basic structure of creating a model and predicting a value, right?
Can I ask a question?
Yeah.
So in this, we are calling model fit, and we're fitting the data, which is like input and the output that we know, or
Mhm.
the model is creating its own output and taking it.
No, we are giving the output we know also.
So we're giving the example of both, so the model
Yeah.
can learn from it. Okay, thank you.
Yeah, this is an example of supervised learning.
Mhm.
So we are giving output y also. Yeah. So yeah, let me we'll dive into what is regression and classification. Okay. So um, regression is to predict continuous numbers in a range of numbers, right? The best example is predicting the temperature, tomorrow's temperature, right? Or predicting the home prices when we give this size of the home price. That's for these kind of problems we use regression. Classification is, you know, the range of outputs, right? Your output. Okay. Classification is a supervised learning task. It categorizes data into discrete predefined classes or labels, right? Um, how many types of classes the output can be, right? One example of, in classification, you have binary classification. Binary classification is to predict between two different classes. Example is you're giving an image and model has to predict whether the image is cat or dog. This is binary classification. Multi-class classification is where it has to classify between three classes or four classes, etc. Example is cat or a dog or a rabbit. So that is multi-class classification. So a best example for classification is predicting between cat or a dog. And another example is predicting if the temperature is cold or hot tomorrow, right? Um, so regression predicts numerical value, classification predicts a category, right? So that is the difference between classification and regression. Um, this is an example diagram of regression. So these are all the data points. All the dots you see are the data points. On x-axis, we have square feet of the home. On y-axis, we have price of the home. You would All these dots is your complete data set. And when you give all your data set to the model, then the model is model. Basically, what is a model? Model is basically in this picture, this straight line is the model, right? It is so the best model is a model which fits the data correctly, right? That's considered a best model, right? When we look at root mean squared error, we will understand more about this. But the formula of the model is basically y is your output that needs to be predicted, x is your input, mx plus b is the formula for the model, linear regression model. So m is the slope, b is the intercept, right? So yeah. So that's the formula of linear regression model. Um, yeah, let me switch. So this is, we'll look at how we create a model, right? So as I showed, we create the model, we fit the model with the data, then we predict, right? It's a simple code. We are creating the model here, we are fitting the data. In this step is where the model learns from the data, then we predict on new input, right? It's the same. You have your feature X, then your output or the target value Y. I would say output, right? And then you are creating a linear regression model here using scikit-learn. You are fitting both X and Y values. Then you are predicting on the new data. So you need to always predict on a data where the data should not be used for training. You should predict on the data which is not used for training, right? So this is an example of supervised learning, right? We discussed about clustering. Clustering is unsupervised learning, as you can see in this picture. So for clustering also similar, right? You were creating the model, you were saying 3 clusters are required. Here, you are providing only the X, you are not providing Y because there is no ground truth for unsupervised learning. And then you try to predict on the new data. Right? So this is an example of unsupervised learning and how we use scikit-learn to create model and predict the values. Right. Then we will look at linear regression. So I want to show, okay. So this is linear regression. The code is similar to create a linear regression model also. I think we already have seen this code. Um, so you can, if you want, you can see what is the coefficient and intercept also. Coefficient is m. In the formula, we have mx plus b, right? M is coefficient, b is intercept. Um, so a simple linear regression model is where your x is square feet and y is price, right? When you train the model on number of square feet and price, and then you provide one more square feet to predict, and it'll predict the price for you. And the important thing is you need to split your data. Yeah, go ahead. I see a hand raised.
I have a question. It's not that related to scikit-learn topic right now, but it's for when we're trying to determine what kind of model do you want to use? Do you want to use a linear model, or maybe it's like a parabolic relationship, or basically we don't know. And like in university, when we came across like a physics kind of scenario where we're trying to gauge what's the relationship between these data points, we essentially have to like try as many different kind of like pairs of formulas and then put everything in there and see if it's matching. Is there any kind of like similar approach in data science where we ask the model, hey, we have this bunch of data, but we don't really know what's the approach, what's the relationship, and then can you go find out how we can translate these two? So it's not quite as um, it doesn't go as far to say that there may be no relationship and just learn what the relationship may look like. It does suppose that there is a relationship. It could be linear, it could be parabolic, but we don't know yet.
Um, I think um, we need to train the model first and then evaluate the performance, right? If it is like underfitting or overfitting, then we try to change the features. That's called feature engineering. And
Yeah.
also try to do non-linear regression like wx squared plus wx plus wx plus b like that. Um, so that's my understanding.
Well, I don't really know the data science side of things too well, but to me, that from like an outsider's perspective, it seems like we are trying to teach the model a way to understand these simple ways of thinking about the relationships between two sets. Like we're trying to teach it, hey, maybe it's not mx plus b, maybe it's ax to the power 2 plus bx plus
Yeah.
c. Maybe, is there like an easier way that we could essentially ask the model or have a model try all of those easy to check scenarios instead of like trying to fit everything into like instead of trying to train the model?
Yeah, so it's um you need to measure the error, right? Root mean squared error. So um based on your root mean squared error, if the error is close to zero, then the model is best fitting the data, right? Let's say you did linear regression and your data is not fitting, your error is not close to zero, then I think you try other approaches. So that's the understanding I have, but I think I need to explore further also on that.
Thank you very much.
Yeah. So so yeah, I was trying to say our data set, we split it as train data set and test data set, and we train the model only on the train data set. We don't expose the test data set to the model during the training phase. And the test data set we use only to test the model's performance. So that's one important thing to remember. And then, okay. So that's train test split, right? And you can split it by using this function train underscore test underscore split. You can tell the test size 0.2. That means if you have 100 samples of data, 20 samples of data is used for test split. 80 80 data is used for training, right? So for evaluating the model performance, as I mentioned, root mean squared error is used. If your root mean squared error is very near to zero, that means your model is really performing well. The error in the model is very less, right? Um, so I want to explain more about root mean squared error. Let me see. I want to show one other picture. I think this is, yeah. So this picture actually gives an understanding on root mean squared error, right? So this is the model. Um, Basically, your model, these are the predicted values of your model, but the green dots are the actual values, right? If you want the model to predict for this X value, it will predict this dot versus this dot. And the error is this dotted line is the error. Error is like original value minus predicted value gives the error, right? And you calculate all the errors of your testing, of your test data set predictions, and then you take the mean of the error and then square root it. Then if the error is near to zero, then your model is really performing well. That means it's fitting the data well, right? Um, so we evaluate the model performance by using root mean squared error. And R2, R2 answers a different question. It basically tells how much better is the model than simply predicting mean value, right? Instead of using machine learning algorithm for prediction, you can just take the mean, right, of the data set as a value if you want. But R2 basically tells compared to mean how good the model is performing. So R2 of 1 means it's covering all together all of the data set you have, um, and predicting the value, right? That means it's a perfect prediction. R2 of 0 means model is not doing a prediction any better than mean, right? Um, so that is about R2. Okay, so yeah, so that is about R2, and the next concept is, sorry. Um, so until now we discussed about one input, which is square feet of the house, right? Let's say house prices, if you have to predict the house price, it may not be just based off of out of the square feet of the home. And there are other parameters you will consider, right? How far the house is from the, let's say, downtown, right? If the house is very near to downtown, the house price will be more. Let's say within 10 miles from downtown, the house price will be more. If it is 30 miles from downtown, it may be house price may be little less, right? So that is a factor to be considered. In other words, a feature to be considered. And you can add that feature also during the training phase, right? Um, and then your model formula becomes this, right? Price equals to B1 into square feet, plus B2 into distance plus C, right? So when you do that, when you consider the distance, what happened is your R2 score is improved because your model is covering more variance. It is covering more data. That means discovering more variance. Here is an example of adding a feature. When distance is added to an input feature while training the model, your R2 score is improved from 0.75 to 0.89. So when we added a feature distance while training the model, the R2 score is improved, the model is performing better. Similarly, one other factor to consider while predicting house prices is if the house is new or not, along with square feet and distance from the downtown, let's say. If the house is new, obviously it'll be priced higher than the old house with the same square feet and with the same distance, right? So when we add one more feature, which is underscore new, then your R2 is increased from 0.89 to 0.94. So we are even more covering more data, more variance, and the model is performing better. Yeah, yeah, go ahead. I see a hand raise.
Okay, my question is similar to the question that was before. How do we distinguish which data to feed the model? Do we do some exploratory analysis or something on the data set that we have? Or we just know, like in the house price, it's understandable. Square feet distance is new as like closely related to the price. But if the data that we know nothing about it, how we distinguish which are more relevant to the model
Yeah.
before feeding?
Um, so this is supervised learning, right? In supervised learning, we know we know the data with supervised learning. With unsupervised learning, we don't know the truth. The truth needs to be determined by the model, right? Um, but let me think, okay, to answer your question. Um, um, yeah, I think I need to check. I'll come back on this question.
Okay, thank you.
Yeah. Let's see what else we have. So yeah, then we have uh, good fitting, good fit and overfit. Overfit is where your model performs well on the training data. When you measure your model on the training data, it'll give good metrics. But when you measure on the test data, it don't perform well. That means it's trying to memorize the data instead of learning from the data. That is an example of overfitting. Um, so underfitting is basically your model is not learning anything. I would say. So that's here is an example graph of underfitting, right? I think that covers the today's session. So in the upcoming session, we look at classification, right? We look at pre-processing before we perform classification, and then we look at k nearest neighbor algorithm and logistic regression. Similarly, we have looked at evaluating a linear regression model in today's session, right? So similarly, we will look at how to evaluate a classification model in the next session. So that is called classifier evolution. Thanks for joining the session. Have a great day ahead.
Thank you.